So this is another video for Advanced Higher Chemistry Unit 3, and we're going to be looking at the technique known as thin layer chromatography, shortened to TLC. So what is TLC? Well, TLC is a technique used to separate mixtures based upon their solubility. So previously we've looked at separating mixtures based on their melting points and their boiling points. Now we're looking at one that will separate them based on their solubility. Now, the thin layer part refers to a layer of silica or aluminium oxide that is spread over a material like glass, plastic, or aluminium. And this forms a stationary plate, so it's stationary phase, and it forms usually a rectangular shape that is thin and it is solid. And you're going to put your compounds onto this plate and then add a solvent that will dissolve your compounds and move your compounds. So the compounds are spotted onto the bottom end of the stationary phase, and then a solvent is placed underneath the spots, and it moves upwards through your silica or aluminium oxide, and depending on whether or not compounds are dissolved in or will dissolve in your mobile phase, the spots will either stay still at the bottom of the plate or will be moved upwards by the solvent. So how does it work? Well, the stationary phase, your aluminium oxide and silica, are usually quite polar. And so anything that's polar will stick to the stationary phase. The mobile phase is usually less polar. It's usually made of either permanent dipole solvents or non-polar solvents completely. Now, depending on the polarity of the compounds, they will either form stronger intermolecular forces with the stationary phase or with the mobile phase, and therefore either want to stay on the stationary phase and not move very far, or dissolve in the solvent and want to move as the solvent moves. So compounds that are not soluble in the solvent don't move far. Compounds that are very soluble move far. Those bottom two lines are better to remember than thinking about polar, non-polar, because thin layer chromatography can be done the other way around, where the stationary phase is non-polar and the mobile phase is polar. The most important thing to remember is that if your compound dissolves in your solvent, it will move far. If your compound doesn't dissolve well in your solvent, it will stay near the bottom. So a chromatogram looks something like this. So you draw a pencil line about 1 centimeter to 1.5 centimeters from the bottom. It needs to be pencil because if you use pen, the pen will contain compounds that will dissolve in any solvent. So you need to use pencil. You then spot your chemicals. So use a capillary tube. Capillary tube just means a really thin tube, similar to the one you would use in a melting point apparatus. You suck your compound up into that tube, and you don't actually need to suck if you just place the tube inside of it. Some compound will naturally suck up through something called capillary action. Then you gently spot that, so lower it onto the line, and compound will actually come out and form a spot on the slide. You've got to remember, most of the chemicals you'll be working with when you're doing TLC are colorless, so you'll only see sort of like a wet patch for your spot at the start, which will eventually dry and your plate will look like it's got nothing on it. When you've done all the spots that you want to test, and sometimes you need to do more than one spotting on top of each other just so you get enough compound in the right place. But once you've got all your spots ready, you're going to gently lower your plate into a solvent. And the solvent needs to start below where the spots are. If the solvent touches the spots before the start of the experiment, what happens is that the spots will just dissolve into the solvent and stay in the solvent at the bottom. You need the solvent to always be below the starting point of your spots. You usually cover your container and then you leave it for the solvent to soak upwards. After a period of time, you're basically wanting the solvent to move not to the top of the plate, but about 1-2 centimeters away from the top of your plate. You'll stop it. You will record the distance traveled by the solvent by making a pencil line at the top, because you're going to need to use that as a reference point. Now, what you've got, so that plate, after the experiment has been done, we'll call it a chromatogram. And at the experiment, you'll mostly only see how far the solvent has moved. We call that the solvent front, and you're going to draw a line to show where that solvent front is. The spots are usually not visible. Only if you're doing chromatography on dyes or inks will the spots be visible. Many compounds, the spots will actually be colorless, and so you need to visualize them in some way. So one of the most common ways is to place them under a UV light. Compounds that are not usually colored absorb UV light instead of visible light, and so if you place them under a UV lamp, the spots will glow, and you can then use a pencil to mark where those spots are. You can also add a developing agent. Developing agents are usually either a reducing or an oxidizing agent that will stain the whole plate, but the spots will end up a different color because they will have done a redox reaction that has changed the color of the stain. And so that allows you to visualize your spots. Once you know the position of the spots, you can calculate something known as an RF value. So RF values. The equation for RF value is the distance traveled by the sample, that means your spot, divided by the distance traveled by the solvent. So it is really important that at the end of the experiment you do mark the distance traveled by the solvent. And that distance traveled by the solvent is the distance between the starting line, the first pencil line where all the spots were, and the pencil line you've used to record where the solvent finished. RF values are always between 0 and 1, and what they basically are percentages representing the percentage of the distance that the solvent travels for the spot. Not sure I explained that particularly well, but as an example, if the RF value is 0.6, it means it traveled 60% the total distance that the solvent traveled. Now, a large RF value, close to 1, means that your compound, the sample, was very soluble in the solvent. A small RF, which means it traveled a very short distance, means that it's not very soluble or less soluble in the solvent. And RF values will change and will be different for different solvents. This is important if you're given a whole load of different RF values and then have done an experiment. You need to make sure you're only comparing like with like. So RF values can only be used if you're looking at experiments done under the same conditions. So under the same temperature, under the same humidity, and most importantly, using the same solvent. So what's the purpose of TLC? Well, it is used to identify compounds. So if the RF value of a spot matches the RF value of a desired compound for the same solvent and temperature, you can positively identify that compound. So that involves looking up a whole load of RF values, looking up the experimental conditions and getting a match. Alternatively, if you've got some pure compound, you can run your sample directly on the same TLC plate as the pure compound, and if they travel the same distance and have the same RF value as a result, you can say that your compound is a match for that compound. TLC is also used for checking purity because pure compounds will only have one spot in a TLC. So for example, if you're doing a reaction, if you have one reactant that's turning into one product, at the start you would have one spot with one RF value corresponding to the reactant. If you were sampling the reaction as it went on, anytime that there are two spots, it means you contain a mixture of reactant and product. When you only have one spot with a different RF value for the product, that's when you can say the reaction has finished and you've produced pure product. So TLC used for identification and checking purity. That has been our short video on TLC.